Hello, welcome to Maths with EJD. In this video, I'll be comparing the methods for solving systems of linear equations. Okay, methods, methods for solving systems of linear equations. Okay, now, in the past videos, I've gone through all the six methods, namely the Gaussian elimination method, Gaussian elimination, elimination. Then I've done lower upper decomposition, that's LU decomposition, because the uh, coefficient matrix of the matrix is decomposed, is factorized into the product of lower and upper triangular matrices. Then we have the Cholesky decomposition, Cholesky decomposition. Then we also looked at the Jacobi method, Jacobi method. Then we saw the Gauss-Seidel method, Gauss-Seidel method. And lastly, interestingly, we saw that Gauss-Seidel method is an improvement on Jacobi method. And we also saw successive over-relaxation, successive over-relaxation. That is the SOR method, SOR method, which is an improvement on Gauss-Seidel, interestingly. So we saw that the first three are seen as direct methods. They are direct methods because you just, do what you have to do and you get the results. And you have the iterative methods. So one question that will always arise is, what's the use of the iterative methods? They are not just there for fun, right? So that's the essence of this video, to compare their performances and to know the best time to use each method. So the last three are known as iterative methods because you have to keep iterating to get solutions. That to get as you keep iterating, the results may be converging towards what you expect, or it may not. It all depends. So let's just do a table and say, look at the method, and then we look at the type. Of course, the type has been taken. Okay, well, since I've talked about the type, let's forget about type. Type is either whether it's direct or iterative. So that has been taken care of at the top. The first three are direct methods, while the last three are iterative methods. So the next one we want to consider will be the computational cost. Like, how fast is it? Computational cost. Then we can talk about the accuracy. How accurate can it be? Then you talk about the stability and suitability. Stability and suitability. When is it suitable to use? Okay, so these are the things we'll be considering. Okay, so let's start with the first one. We take the first one. Let's talk about Gaussian elimination. Gaussian elimination. What is the computational cost for Gaussian elimination? It is cubic in nature. So it's the time complexity is O9 cube, big O9 cube. That's something in computing to show how fast it converges. So it is not linear, it is not quadratic, it is actually cubic. Then accuracy is high. Of course, you're assured of getting the exact answer. Then we have for stability, it is quite stable. And suitability, it is best for small systems. Best for small systems. So if the system becomes very large, it may not be so suitable anymore. Okay, so it's best for small systems. That is about Gaussian elimination. So let's talk about the next one, which should be LU decomposition. LU decomposition. So we have LU decomposition. Again, Okay, maybe it's because of this system that is ON3. I think because of the particular problem we solved, right? Like given the particular problem, that 3 by 3 system we solved, that's why it may be ON3. So if we have a bigger system, it may not be the same. So we solved the 3 by 3 system, x plus 2y plus 3z equals 9, and 2x plus 5y plus 6z equals 18, and 3x plus 6y plus 14z equals 30. So for that, that's why that's what this computational cost is meant for. So this is big O n cubed. So it's cubic and it's ones. Okay. So the accuracy is high, like we know, we get the answer directly, and it is definitely stable. There's no worry, we get an answer. It's best used efficient for repeated solutions with same matrix. Okay, so it is efficient for repeated solutions or repeated solutions with same matrix. Okay, that's when early decomposition is really good to use. So let's go for the next one, which is Cholesky decomposition. So I mean, Cholesky has a bit of issue. You have to be sure it meets certain condition. So you have Cholesky decomposition. Okay. Now it also goes ON3. I believe it's because of the 3 by 3 system, most likely. Then the accuracy is high. Then the stability requires symmetric positive definite. If not, you can't guarantee its stability. It requires the matrix to be symmetric and positive definite. You remember when we did that example, we talked about that. So it's only suitable for symmetric and positive definite matrices. So that we saw that when we did Cholesky. So you have to first of all make sure that your matrix is symmetric, meaning that the original matrix is the same as its transpose. That is the idea of symmetricity. Then we now have the next one, which is Jacobi method. We have Jacobi method. So for Jacobi method, right, the time complexity is O n squared K. Okay. And the stability is moderate. You can be sure. Like, in fact, the particular one we did, we saw the solution to be diverging. So the accuracy is moderate. The stability, it can be slow, right? It can actually be very slow, can be slow. And talking about suitability, only for symmetric. No, yeah, it can be slow, then parallelizable, suitable for diagonally dominant matrices. So it is para, it's parallelizable, okay, and then it's parallelizable, suitable for diagonally dominant matrices, okay. Then that's about Jacobi. Then we go for Gauss-Seidel method. So Gauss-Seidel method. So for Gauss-Seidel method, right? So the time complexity again is 0 n squared K. Then the accuracy is moderate. The accuracy is moderate. Then for its stability, it's faster than Jacobi. Faster than Jacobi. Faster than Jacobi. Then good for diagonally dominant, diagonally dominant, or diagonally dominant, or well-conditioned matrices, or well-conditioned matrices. Okay. All right. So the last one, of course, is successive over-relaxation. Successive over-relaxation. Oh no, this is another marker, right? Just want to follow that pattern. Yep. So successive over-relaxation method. Okay. So the time complexity again is O n squared K. Then the stability is stability now. Accuracy is moderate to high. Moderate to high. What am I doing? Should Okay, I want to keep the color thing. So O n squared K, that's the time complexity. The accuracy is moderate to high. And then the stability is, it's the fastest among iterative methods. Okay, but you have to get the omega right. Fastest among iterative methods. It is supposed to be right among iterative methods. Then it's suitable for systems where relaxation accelerates convergence. Suitable for systems where relaxation accelerates convergence. Okay, so those are the methods right there. Now, can we talk about some key takeaways? Key takeaways. So if you are interested in numerical, it's a field. Some people are experts at numerical analysis. Okay. So one takeaway is that Gaussian elimination, Gaussian elimination, LU decomposition, LU decomposition are, so these two are direct methods. They are direct methods. They are best for small to medium-sized systems, small to medium-sized systems. Okay, that's that. Then we have number two takeaway is that LU decomposition, LU decomposition is efficient when solving multiple right-hand sides, multiple right-hand sides. For instance, if you notice the practice question and the question we've been solving, one of the practice questions are basically the same, except that the right-hand sides are different because those variables can have the same thing for a particular kind of system. Okay, so good for multiple right-hand sides. So you have the number three takeaway. It is that Cholesky decomposition, Cholesky decomposition is optimal it's only optimal for symmetric positive definite, symmetric positive definite, and that's SPD for short, symmetric positive definite matrices. Okay. Then we have the fourth takeaway is that Jacobi method is simple and parallelizable. Can parallelize it, parallelizable, but slow to converge. So it can be quite slow, but slow to converge. Then you have the fifth takeaway. The fifth takeaway is that Gauss-Seidel method improves upon Jacobi by using updated values. And number six, successive over-relaxation is the fastest iterative method. It is the fastest iterative method, but there's a condition, right? I mean, it's fastest iterative method, improving Gauss-Seidel by using a relaxation factor. Okay. So in conclusion, so point one is that use direct methods. We know the direct methods are Gaussian elimination, LU decomposition, and Gaussian elimination, LU decomposition, Cholesky decomposition. When use them when computational cost is not a concern. So if you don't have a problem with computational costs, you're good to go. Then two, now you see the use for iterative methods now, because you can actually see it may look like it's actually, what's the use for iterative methods when you have direct methods? So use iterative methods like the Jacobi method, Gauss-Seidel method, or the successive over-relaxation method. Okay. For large, if you have large sparse systems, so you can have sparse systems where many values are missing. Large sparse system where efficiency is key. So if you need a lot of efficiency, where efficiency is key. Okay. And lastly, the third conclusion would be that successive over-relaxation is preferable among iterative methods, due to faster convergence, And I've shown you the Python code for each of them. If you have not seen it, you can follow my handle on Facebook. I'm not able to put the code. I thought I would be able to put the code on YouTube. I'm not able to do that in the description because they don't take maybe angular brackets or something like that. But if you check the caption on Facebook, at the base of or whatever, you'll find the code for each of these implementations, both direct and iterative methods. So if you have subscribed to the channel, thank you very much. If you haven't subscribed, please go ahead and do that and hit the notification bell so you can always get alerted each time a new video is released. Comment. I've given you some practice questions. In fact, let me repeat those practice questions. Okay, I'll just write the 3 questions. Okay, well, check previous videos, right? Check previous videos for practice questions, and feel free to comment your answers with in the comment sections, and let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. Then like and share so that more people can have access to this great learning. Till I come your way again, keep doing maths right. Of course, numerical analysis continues. I'll be talking about eigenfactors and eigenvalues and eigenvectors, the applications, and so on and so forth. It's going to be a long series, I believe, a long playlist. So be sure to be glued to the channel so you don't miss out on anything. Till I come your way again, keep doing maths right. Bye.